Hello, we shall start chapter 5 module 6. In this module, we shall concentrate on the famous theorem called Tychonoff product theorem. We have already known that finite product of compact topological spaces is compact. Here, we shall prove that arbitrary product of compact spaces is compact. First, we shall prove that countable product of sequentially compact topological spaces is sequentially compact. But unfortunately, arbitrary product of sequentially compact spaces may not be sequentially compact, which will be improved by proving that arbitrary product of compact topological spaces is compact. In fact, in proving this theorem, Jones' lemma will be a necessary part. We require the Jones' lemma or axiom of choice to guarantee that arbitrary product of non-empty set is non-empty. Moreover, this theorem, that is Tychonoff product theorem, also proves that the axiom of choice. That means if we assume that arbitrary product of compact spaces is compact, then it will prove that axiom of choice. This was due to Kelly. Let us come to the slide presentation. So, let us start the proof of Tychonoff product theorem by recalling the product topology. Let X alpha F alpha be a given collection of topological spaces and X is equal to product of X alpha be the Cartesian product of X alphas. That is, X is the set of all tuples X alpha alpha belongs to the index set gamma, where each X alpha belongs to capital X alpha. We recall that X is non-empty when each X alpha is non-empty. This follows from the axiom of choice. In fact, in case of countably infinite product, since we can enumerate any countable set, so this is easy to think of an element in capital X, but this is not possible to construct an element in X when the index set is uncountable. Here axiom of choice works. Axiom of choice guarantees that X is non-empty. We also recall that projection maps pi alpha from X to X alpha are defined as pi alpha of X is equal to X alpha. Now, product topology on capital X is the smallest topology which makes each pi alpha continuous. We can say also in this way that if we take all possible pi alpha inverse u alpha where alpha belongs to gamma, then this collection forms a subbase for some topology, and the topology generated by this collection as submesh is in fact the product topology. In this connection, let us recall the definition of box topology. Box topology is in fact consists of basic open sets of the rectangular form. That means a basic open set of box topology is of the form product of U alpha, where alpha belongs to gamma. But unless otherwise stated, we always consider product topology. In fact, box topology is too large to consider. Box topology is so large such that the sequence 1 by factorial m e to the power minus n m, n is equal to 1 to infinity, does not converge to the 0 sequence in the product r to the power n when considered with the box topology. But in case of product topology, the situation improves. So, we shall prove the Tychonoff product theorem in case of product topology. Let us first prove that sequential Tychonoff product theorem, which says that countably infinite product of sequentially compact spaces is sequentially compact. Let xn tau n be a countable family of sequentially compact spaces and consider the product spaces product of xn, n is equal to 1 to infinity with the product topology. Let x1, x2 be a sequence in X. Here x1, x2 all are points of X. That means x1 is a tuple x alpha, alpha belongs to gamma. Similarly, x2 is also a tuple of such that x2 is equal to y alpha such that alpha belongs to gamma. In this way, now we wish to show that this sequence has a convergent subsequence, say x mj in capital X, which converges to some limit x is equal to xn, n is equal to 1 to infinity in the product topology, where each xm is itself a sequence xm is equal to xnm, n is equal to 1 to infinity with xnm belongs to capital Xn for all n. Consider the first coordinate of the m term of the given sequence, that is pi 1 of x m, which we denote by x1m, and this is in capital X1. Thus, we get a sequence x1m in capital X1, and as x1 is sequentially compact, we can find a subsequence x m1j, j is equal to 1 to infinity in capital X, such that x1 m1j converges in x1 to some limit x1 belongs to capital X1. Now, In this subsequence, consider the second coordinate x2 m1j in capital X2. As X2 is again sequentially compact, we can find a further subsequence x m2j, j is equal to 1 to infinity in capital X, such that x2 m2j converges in x2 to some limit x2 belongs to capital X2. Also, we inherit from the preceding subsequence that x1 m2j converges in x1 to x1. We continue in this vein, creating nested subsequences x mij, j is equal to 1 to infinity for I is equal to 1, 2, 3, whose first I components are x1 mij up to xi mij, converts to x1 belongs to capital X1 up to xi belongs to capital Xi respectively. None of these subsequences by themselves are sufficient to finish the problem, but now we can use the diagonalization trick. We consider the diagonal sequence x mjj, j is equal to 1 to infinity. One easily verifies that x n mjj converges in xn to small xn as j tends to infinity for every n, and so we have extracted a sequence that is convergent in the product topology. This proves the fact that countably infinite product of sequentially compact spaces is sequentially compact. But uncountable product of sequentially compact spaces may not be sequentially compact. For example, consider the product spaces 0, 1 to the power 0, 1 to the power natural number. That means all functions from 0, 1 to the power natural number to the set 0, 1. As singletoned 0, 1 is sequentially compact, in fact compact with discrete topology, this is an uncountable product of sequentially compact spaces. On the other hand, for each n belongs to n, we can define the evaluation function fn from 0, 1 to the power n to 0, 1 by fn from m is equal to 1 to infinity to an. This is a sequence in capital X. We claim that it has no convergent subsequence. In fact, given any nj tends to infinity, we can find x is equal to xm, m is equal to 1 to infinity, belongs to 0, 1 to the power n, such that xnj is equal to fnjx does not converge to a limit as j tends to infinity, and so fnj does not converge pointwise, that is fnj does not converge in the product topology. Hence, we can say that uncountable product of sequentially compact spaces may not be sequentially compact. So we have seen that countably infinite product of sequentially compact spaces is sequentially compact, but for arbitrary case this result may break. That means uncountable product of sequentially compact spaces may not be sequentially compact. In case of compact spaces, the situation improves dramatically. For compact spaces, arbitrary product of compact spaces will be compact, which is called Tychonoff theorem and will be proved in our lecture. In proving the Tychonoff product theorem, we again use the result that every filter can be extended to an ultrafilter. Here we shall prove that every filter can be extended to ultrafilter. In fact, still now we have not proved this result. So let us consider the following lemma. Let capital X be a set and script A be the collection of subsets of X having the finite intersection property. Then there is a collection script D of subsets of X such that script D contains script A and script D has the finite intersection property, and no collection of subsets of X that properly contains D has this property. That means script D is maximal with respect to having finite intersection property. To prove the theorem, we shall use the following notations. By small English letter, we always mean a member of the topological space capital X. By capital English letter, we shall mean subsets of the topological space X, and by script English letter we shall mean collection of subsets of the topological space X. Now by hypothesis we have given a collection script A of subsets of X that has finite intersection property. We wish to find a subset of X which has finite intersection property, which contains script A and which is maximal with respect to finite intersection property. Let blackboard bold A denote the superset consisting of all collections script B of subsets of X such that script B contains script A and script B has the finite intersection property. We use proper inclusion as our strict partial order on A. Under this inclusion relation, blackboard bold A is a partially ordered set. To prove our lemma, we need to show that blackboard bold A has a maximal element script D. In order to apply Jones' lemma, we must show that if blackboard bold B is a superset of blackboard bold A, that is simply ordered by proper inclusion, then blackboard bold B has an upper bound in blackboard bold A. We shall show in fact that the collection C is equal to union of script B, B belongs to blackboard bold B, which is the union of the collections belonging to blackboard bold B is an element of blackboard bold A. Then it is the required upper bound on blackboard bold B. To show that script C is an element of blackboard bold A, we must show that script C contains script A and that script C has the finite intersection property. Certainly, script C contains script A, since each element of script B contains script A. To show that script C has the finite intersection property, let C1, C2, Cn be elements of script C. Because script C is the union of the elements of blackboard bold B, there is for each I an element script Bi of blackboard bold B such that Ci belongs to script Bi. The superset script B1, script B2 up to script Bn is contained in blackboard bold B. So, it is simply ordered by the relation of proper inclusion. Being finite, it has a largest element, that is, there is an index k such that script Bi is contained in script Bk for I is equal to 1 to n. Then all the sets C1, C2, Cn are elements of script Bk. Since script Bk has the finite intersection property, the intersection of the sets C1, C2, Cn is non-empty as desired. Now we come to our final theorem. Arbitrary product of compact space is compact in the product topology. To prove this, let X be the product of X alpha where each factor space X alpha is compact, and let script A be a collection of subsets of X having finite intersection property. We wish to prove that intersection of closure of A where A belongs to script A is non-empty. That means we wish to prove that any collection of closed sets with finite intersection property has non-empty intersection. Now, applying the previous lemma, let us choose a collection script D of subsets of X such that script D contains script A and script D is maximal with respect to finite intersection property. It will suffice to show that intersection of closure of D such that D belongs to script D is non-empty. Given alpha belongs to J, let pi alpha from X to X alpha be the jth projection map as usual. Now consider the collection pi alpha D such that D belongs to script B of subsets of X alpha. This collection also has finite intersection property as script D has the finite intersection property. Now, by compactness of x alpha, we can for each alpha choose a point of x alpha such that x alpha belongs to intersection of pi alpha d bar, where d runs in script D. Let x be the point x alpha, alpha belongs to j of capital X. We shall show that x belongs to d bar for every d belongs to script D. First, we show that if pi beta inverse u beta is any subbasis element for the product topology on X containing X, then pi beta inverse u beta intersects every element of script D. Since the set u beta is a neighborhood of x beta in capital X beta and x beta belongs to pi beta d closure, we have that u beta intersects pi beta d in some point y pi beta y, where y belongs to d. Then it follows that y belongs to pi beta inverse u beta intersection d. Now, every subbasis element containing x belongs to D, and then every basis element containing x belongs to D. Since D has finite intersection property, this means that every basis element containing x intersect every element of D, and hence x belongs to D bar for every D belongs to script D. Hence, we have that intersection of closure of D such that D belongs to script D is non-empty. This completes the proof of Tychonoff product theorem. We end this module by mentioning the fact that Tychonoff product theorem in fact implies axiom of choice, which you can see from this note. In this module, we have proved one of the most important topological theorems called Tychonoff product theorem. This theorem is in fact equivalent with axiom of choice. With this theorem, we end this module. Let us pass to next module.